Okay, that's going to lead us to our next speaker, Martin Hoymakers from Ansys. So we'll go ahead and he should be coming in any moment. All right, there he is. Hi, Martin, can you hear me?
Hi, Kelsey, I can hear you fine. Can you hear me?
Wonderful. Okay, so I'll go ahead and let you take over the screen, and then our audience members, the attendees, are sending a little thumbs up when everything is good, okay?
So I think I'm sharing, so please confirm.
Alrighty, I see some thumbs up. We are good to go. Thank you, Martin.
All right, perfect. So thank you, Kelsey, for the introduction. And so my name is Martin Hoymakers. I'm an R&D engineer at Ansys. And today I will talk a little bit about our hard modeling activities using LS-DYNA. So first, let me start by just briefly introducing our team. So 2-3 years ago, Ansys decided that they would start a dedicated healthcare R&D team that would be working on various clinical applications. And by now, that team sort of has grown to about 6 full-time employees, managed by Michelle Rochette on the top here. And besides our full-time employees, we also have several interns and PhD students that are working on several funded projects together with our academic and clinical partners. So the mission of our team is really the democratization of simulation for 2 markets, so the medical device industry and for clinical applications. So for clinical applications, you can think about cardiac arrhythmias, ECG inverse problems, or electromechanical digital twins. So our work is really to use Ansys solutions and Ansys products to build clinically relevant models. And at the moment, we have a focus on the heart because that's a very challenging and relevant topic. But in general, we are interested in clinical applications. So if you have any, please get in touch with us and we can see if we can help each other. So one thing here is that we want to make sure that we can personalize and validate these models by using clinical and in vitro data. So in order to do that, we also actively engage with sort of ecosystem, so with academia, hospitals, and industrial partners. So just to be clear, so our goal is not to develop a sellable heart model, but our goal is more to develop a flexible platform that would allow you, so the users, to actually use our tools to build their own heart models using products from our portfolio. So why heart modeling? And so why our focus on heart modeling? So heart disease is the leading cause of death in the Western world. So about 1 out of 4 or 1 out of 5 deaths is related to heart disease. And there has been a lot of effort by the computational community to try and build models that can help try and alleviate that burden. So either for medical device companies to develop better devices and develop these devices faster, or for clinicians to improve their diagnosis and to improve their therapies. So I've show here on the bottom left two examples. So we have a left ventricular assist device. So a medical device company would be interested in trying to see how that medical or left ventricular assist device sort of interacts with the beating heart or the pathological heart. So that would be one application. Another more clinical application would be left bundle branch block. And here on the bottom right, you see a sort of simulation of electrophysiology where the left heart here is sort of not functioning properly because we have the bundle branch block. And this shows the sort of pacing strategy that can sort of restore the activation of this heart muscle. So this is an academic paper, so you can go here on the bottom left. So this is also being done by one of our academic partners. So for heart modeling, we really need 3 types of physics, or 3 types of physics are relevant. So we have electrophysiology, mechanics, and fluid mechanics, and these are all coupled in a specific way. So that makes it a very challenging topic or application for us. So we need to have the core technology available to sort of solve the governing equations. So for the fluid dynamics, we have the Navier-Stokes. We need to implement the equations that govern the response of the tissue, but also those of that sort of govern the evolution of the transmembrane potential over time and over space. And in the normal in vivo heart, these are all sort of coupled together and are interacting with each other. So for some applications, we may need to couple these kind of physics as well. So it's really a multi-layer approach. So once we have this core technology available, we also need to build features on top of that. So you can imagine that when we image the heart, this heart is sort of under stress because it's filled with blood. And before we can start a simulations, we need to compute the stress-free shape. So essentially when the heart is completely empty. So we've implemented methods to be able to compute those kind of stress-free shapes. On top of that, we need to consider different strategies for boundary conditions. So the heart is it's pretty peculiar because it's sort of suspended in this fluid-filled sac that sort of constrains the motion of the heart. You have different strategies to sort of get the same kind of behavior in your model. So we try to implement some of those strategies. For electrophysiology, we need to consider the heterogeneity of the cells. So some cells behave differently than others. So we need to consider that in our models as well. And from a structural perspective, we need to consider the fibers, because these fibers, these muscle fibers, we cannot directly get these from imaging data. We need to sort of compute these with a rule-based method. So once we have the heart shape, we still need to compute the likely orientation of these fibers. And in a similar way, we need to compute the Purkinje network. And the Purkinje network is sort of channels where the conduction velocity is higher than in other parts of the tissue. So once we have these features, we can think about pre and post-processing steps that we are specific for heart modeling. So we need to extract the different parts. So the heart consists of the left and the right ventricle, but also the atria. And we have the endocardium that needs different boundary conditions from the epicardium, etc. So that requires some different, some specific pre-processing methods. Also to extract that kind of information from imaging data. And for post-processing, we need to extract the right kind of information that makes sense from a physiological point of view. So the physiological quantities, and visualize these in a sort of intuitive manner. Furthermore, there are standardized ways to decompose the heart in different parts. So also that we need to take into account in this sort of modeling layer. So once we have the core technology, the features, the pre and post processing methods, we can start to think about workflows. And with workflows, I mean going from the imaging data, so the patient data, to simulation outputs. So we have to consider, of course, the shape of the heart, but not just that. We also need to sort of manipulate the model parameters to get the same behavior of the simulation as what we observe in the heart. So we need to estimate, for instance, the passive material properties, but also the active material properties, some system parameters that we need to estimate as well to get the right hemodynamics. So that's from a mechanical point of view. For electrophysiology point of view, we need to do sort of the same thing, or we can do the same thing, where we can sort of tune the electrophysiology simulation to match the recorded ECG signal. And this is sort of a back and forth process where we tune the electrophysiology simulation a little bit, and we get a different ECG signal. Okay, we compare the ECG signals, and then we change that again. So it's important to know that this is all still pretty much in the research phase, so it's not really fully, completely developed and ready for the market, but this is something that we are working on actively together with our academic and clinical partners. And to sort of facilitate the use here as well of our solvers, but also these kind of features. We are developing Python APIs and packages to sort of facilitate the usage. So, and also to more easily integrate that in workflows by users. So once we have all that, we can start to think about applications. So I've show a few here, so 3 of them. So previously we've worked with a small image processing company called LS-3D that was able to extract sort of scar tissue or region of scar tissue from MRI data. And from that kind of data, we also built models of the electrophysiology. And questions that are then relevant is, okay, so how do the fibrotic zones affect the depolarization wave that you can compute but not observe in the MRI images, of course? Do we observe any re-entry? What are some candidate sites for ablation? Another application would be cardiac resynchronization therapy, so pacemakers, essentially. So how do we improve patient selection? Because there's a lot of patients that don't respond to treatment, so about 30% of them. And how can we optimize these, the COT parameters to sort of give better clinical results? So in that you can think about lead location or the timing of the stimulation. So this also comes from an academic publication, so it's free for you to see what they did. And then the last one is, for instance, transcatheter aortic valve implants. Much like the work that FEOps is doing, you can sort of do a virtual implantation of a valve implant to see how that affects paravalvular leakage or could cause bundle branch block. So I have 2 more slides, so I think I'm still well within time. So this slide is just to show you an ongoing project that we have with Ansys. So Ansys is again a medical or an imaging processing software company, let's say, that has a few tools available to post-process sign MRI images. So they can, with sign MRI, you have sort of a very limited number of slices. So you have a few long axis slices and a few short axis slices. And what they do is they sort of delineate those slices, and they can provide you with a point cloud that's moving over time. And from this point cloud, we build a heart model, and we try to tune this heart model in such a way to obtain this sort of the same sort of motion as they get, or to get the same kind of data that they get from the images. So to summarize, heart modeling, in our opinion, really has the potential to help medical device companies and clinical practice. They already do, but we think there's much more potential. Also, when you think about, for instance, in silico clinical trials using virtual cohorts, as we've seen in some of the presentations. And for heart modeling, we really have a multi-layer approach. So yes, we have the core solver technology, but we also need to build a lot of features and pre and post processing methods to make it easier to use for the user, and make it tractable for some of these sort of clinical applications. And this sort of opens up the avenue for different applications, such as ventricular tachycardia, CRT, valve repair, etc. Of course, there's still some challenges. So personalization is still a big issue. I mean, we can get the anatomy from 3D images pretty well nowadays, but then taking that data and trying to tune that heart model to get the same behavior as the patient is still a challenge, because you simply have so many parameters that sort of affect the behavior of your model. So the strategies there are not really clear yet. So there's still ongoing research, I would say. And another challenge is to get really physiologically realistic and validated results. And you would have to get those for each of the applications to be actually usable. And finally, of course, we need to understand if and how it has value for clinical practice. And I've added this point like 1 minute ago when I heard Hans mention that about real-time simulation. And of course, that's also a big issue where we cannot rely on, we cannot expect clinicians to wait 1 or 2 weeks to get simulation results. We really need a real-time solution. So we need to sort of combine a data-driven approach with a physics-based approach. So with that, I would like to conclude my presentation, and I'll give the floor back to you, Kelsey. Thank you.
Wonderful. Thank you so much, Martin. A question from my end. So I know you said this is kind of still in the research phase. Do you have a timeline when it might be available to cardiologists at the bedside, or?
To cardiologists at the bedside? Well, I'm not sure, but it depends a lot on the kind of projects you can set up with, for instance, startup companies that can take risks in developing these kind of applications, and how easy it's accepted by clinical practice.
Yes, and then also keeping the end user in mind that
absolutely,
that it's easy to do quickly at bedside and easy for the physicians who don't have time to do software development on the side.
Yeah, absolutely. So that's still very much an open question, and I think there's a lot of papers that show that it has value, these kind of models.
Absolutely.
But it's a long road to get it clinically accepted. So I don't dare to give you any timeline on that. So.
Yes, that's quite all right. Just a question on my end, kind of piggybacking on the question in our previous session. So thank you so much, Martin. It was a very interesting presentation. And yes, so I'm going to go ahead and turn the floor over to our next speaker.
Thank you.
Thank you, Martin, so much. All right.